organic chemistry first lecture in this series. We advise you to go onto the internet and get a copy of Volhart's book. Here it is on Amazon. So here it is on Amazon, Organic Chemistry, Structure and Function by Peter Volhart. You can find it relatively easy with a search, and you can see this version, the more current version, 2014 I think it is free on Kindle. If you don't have a Kindle, which most of us don't, you can download an emulator and still open the book. And this is a good way, and entirely legal way, of getting hold of a very good organic chemistry textbook. If you would prefer a paper version, I would advise you not to spend the full money for the current version and to get an earlier one, like this one for example, an older version which is a lot cheaper. You can also get a second-hand one in some cases, because obviously it's been a standard textbook for a long time, so there are a lot of these floating around. So now we've got that, I would just like to start off with a little bit of standard drawing nomenclature. So if we start off with a molecule, let's say it's got an formula function of formula of CH2, which we could measure using mass spectroscopy or some other analytical technique that tells us how many carbons we've got in there compared to hydrogens, and that there aren't any other elements in our compound. But it doesn't tell us what the compound actually is, because it could be any multiple or fraction of this formula. And so therefore we can have the next most useful or more useful way of drawing it, which would be C6H12 for example. That's an equivalent formula. This could be the same. Doesn't have to be, but this could be the same. This tells us how many carbons we've got and how many hydrogens we've got, but not how they're arranged. So let's draw them better, and let's have a ring because it's fun. So let's have a ring. Every carbon has to have 4 bonds, unless something interesting is happening. So let's have CH2, 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 and one up here, CH2. So this is another way of drawing the same molecule. But in organic chemistry, we discover that this becomes very irritating after a while, because we've got to draw a lot of letters. So we have a convention where we don't write hydrogens, they're implied. So if there are any bonds left over on our molecule that aren't accounted for by charge, extra electrons that we've drawn in, or bonds, then they are hydrogens. So we just leave all of the hydrogens out. There's usually a lot of them. And we don't write carbons either. They are denoted by there being a corner in the molecule. So we can say this is equivalent to, just trying to avoid that bit of brightness there, this is equivalent to a hexagon. So this is cyclohexane, this is cyclohexane, this could also be cyclohexane, and so could this. This is our cyclohexane, which could be drawn like that, with the implied hydrogens, 2 of them on each corner to saturate the carbons, which are on the corners but not labelled. And normally these carbon-carbon bonds are not 120 degrees, so this is not flat. And we can show that with the next way of drawing it by showing that this corner here is high compared to the others, and this corner is low compared to the others. And we normally draw that by making it get bigger as it comes towards us. So let's do that. Let's draw the 2 that are flat. Oops, they are in the plane that we're drawing in, so paper, or in this case a whiteboard, and then they come towards us. And these they're easier to draw open on a whiteboard. They're often easier to draw shaded with pencil or pen on a piece of paper. Let's draw them like that, so they're coming towards us. And the other one is going away. Obviously that's got to get lighter as it goes away because they're further away. And that is shown by drawing a series of dashes. So let me draw that. That's a little bit difficult to get to work on this because my pen's too thin. So I'll do it like that and like this. Are they going to join up? Just about. So this bond is below us or away from us in this case because it's vertical, away from us, and this bond is coming out towards us, showing us that this is a bent hexagon. If we drew it from the side, which is another way of drawing it, we would see that it is this form of a hexagon. So if we take a carbon center, we will see that we've got some 1s orbitals and a 2s orbital and some 2p orbitals, 2p. And the 1s orbitals are quite far down in energy and they don't really participate in bonding, so we're interested in these electrons in here. 1, 2, there are 4 of them. We can draw 1 in each. It's not exactly how they'll arrange. If we take those electrons, or these orbitals, and we add them together, and then divide by 4, we end up with 4 new orbitals. So if we have all of those, is equivalent to 4 times, and the way we write this is sp3. It's spoken sp3, it's written cubed. It's not really cubed because there are only 4 of them. I'm going to have to draw them here. So normally the p orbitals are like this, and there are 4 of them, and they are in an octagonal structure, and the s orbital is in the middle as a sphere. About this, it's a bit bigger than that. But if we take 4 orbitals and we minimize their energy, and we do the maths, quantum mechanics maths of doing that, we come up with 4 orbitals that look like this, with one big lobe and a small lobe with the atom in the middle, not in the middle, in this point here. And if we have 4 of those, they form a tetrahedron. A tetrahedron is a shape difficult to draw, which I always mess up. So this shape much like that. So a tetrahedron is a triangular based pyramid with one of these at each corner, which if we take something simple like methane, we would have a carbon in the middle and 4 hydrogens on the corners. Or if we take something like diamond, so these are bonds, if we take something like diamond, the carbons are connected to each other in a tetrahedral fashion. Whoops, sorry about that one. In the tetrahedral fashion, let me rub that out and come back to here. The carbons are connected to each other in a tetrahedral fashion. Carbon like this. So that makes a diamond a very strong structure, and it's very symmetrical. That's also why the cyclohexane typically doesn't sit flat, because it would have to have 120-degree bond angles, and the angles in a tetrahedron, so in our diamond, are not, they're 109-ish. Another way to reorganize the orbitals in our carbon, the two orbitals in our carbon, would be to take the s orbital, the 2s orbital, and 2 of the p orbitals, and add them together, divide by 3, and leave one of the p orbitals on its own. So that would give us sp2 plus p, and we need to draw that as well. That would be 3 orbitals that also look like this. And because there are 3 of them, they can lie in a plane in a little equilateral triangle structure, with the little heads between the legs, and the p orbital in the other plane. So let me draw that in as 3 in a plane with the p orbital. So this is the extra p orbital, and these are the 3 sp2 orbitals. We will see that in things that have a double bond, like ethene, or something like graphite. So let me rub this out and come in with ethene. So ethene we would typically draw like this. Well, you might typically draw like this. As mentioned earlier, it would just be an equal sign. In organic chemistry, whoops, drawn that too small. It would be an equal sign is equal to an equal sign. And if we draw it with our orbitals, this carbon has 3 sp2 orbitals, which are connected to the carbon, the hydrogen, and the other hydrogen, and it has a p orbital which sticks up and down, which makes up, let's put one on here as well because they're the same, which sticks up and down, which makes the double bond. The double bond is weirdly on the outside. We'll come to that in a little bit. Equally, graphite, the other version of carbon, has carbon at each corner of a hexagonal structure, as we know if we've watched the news, because graphene has been in the news an awful lot. So this will be the carbon. This one is the only one that's filled up. This one and this one are the only ones that are filled up, but never mind. Let's have this carbon here. It has 3 sp2 bonds, which are the ones that we've drawn in, sp2 orbitals that are connected to the other carbons, and 1 p orbital, which is sticking out and into the plane, and that's connected to the others in some way, which we will come to later. And as you would expect, there's a third version that is simply an S and a P, so let's have sp plus 2 p orbitals, and that we would find in something that has a triple bond or has 2 double bonds. So we would have our we need one of these to connect to something, and we've got 2 p orbitals which we can just about draw on there as well. Let's have the p orbitals. Let's have the sp orbital in red, so you can see that that one's different. So that sticks in this direction, and we would see that in something like acetylene, for example, which would be C triple bond C, where we would have another carbon over here which is connected to this one, and then there's a double bond here and a double bond here. These 2 p orbitals are doing the extra bonding, which brings us nicely to how bonding can be explained with this particular model. So let's take a simpler version. Let's take chlorine. So we've got a chlorine atom with a whole load of orbitals, but the one that's going to do the job is one of the p orbitals. So let's just draw that one. That makes drawing simpler. Let's have it here. And we have another chlorine, so let's start with Cl2. Those are the bonds those are the orbitals that are going to participate in bonds. They've got an electron in each, and we will allow them to add together and divide by 2. We've established just now that we can add orbitals together and make new ones, but we always get the same number of orbitals back that we put in, just a different shape. So in this case we're taking an orbital from this this chlorine and an orbital from this chlorine, adding them together and getting two new orbitals, a bonding orbital, which is lower in energy, and an anti-bonding orbital, which is higher in energy. And these 2 electrons, we can rub them out, go into the bonding orbital down here. I think you know that already, but let's get on to the shape of the bonding orbital. So this is a p orbital bond, and it is mostly in between. So we had this plus this, which goes to a bonding orbital in between. This is this one, and the rest of it is the anti-bonding orbital, which is this one, which is a higher energy. And if we put electrons in there, it is worse than having them doing nothing. And that would be, there's a good place to draw that, below. That would be on the outside of the bond, which is easy to rationalize because these atomic cores are positively charged. So if the electrons are in the middle, we'll have plus, minus, plus, and they'll be attracted to each other and hold together as a molecule, the chlorine molecule. If we have the electrons on the outside, they'll be attracted away. So we'll have minus, plus, and minus, plus, and that will pull our molecule apart. This is important because if we want to break this bond, we either have to take these electrons into the neutral state, or we have to take one of these electrons and put it into the antibonding orbital. The third thing we could do is put 2 electrons into the antibonding orbital. In all of these cases it will be energetically equivalent to the starting state, because this bonding orbital is exactly the same amount lower in energy as the antibonding is higher in energy. So if we take this chlorine and we excite one of these electrons up to here, so we take the chlorine molecule and we excite one of the electrons up to there with light. It takes green light to do that. We will show how to denote that in a moment. Then we got 1 electron in the antibonding orbital here and 1 electron in the bonding orbital here, which is equivalent to the chlorines not being connected at all, and so they can wander off and form 2 chlorine radicals, which are 2 chlorines completely separate from each other, and they've got a spare electron. So let me try to draw that. Let's get rid of this. They've got a spare electron, so they have 1 electron each, which is left over, and that's a very unusual state. It's a radical. So when we come to carbon-carbon double bonds, carbon-carbon triple bonds, we have first the single bond in the middle, which is some kind of sp hybrid. So if we take let's take sp2 plus p. We've got this one, which is an sp2 hybrid that has a bonding orbital in the middle and an anti-bonding orbital out here. We need to rub that out so that we will now replace with a line to save space. So this is our carbon. Got a line, or we've got the other carbon, and then also, I need to rub this out too. Then also we have 2 p orbitals, which are going to add together to form a bonding orbital and an anti-bonding orbital. But in this case, the second bond is going to have a similar geometry, so it's got to be above and below the carbon. So we've got to have some kind of electrons here and some kind of electrons here in the bonding state, and in the anti-bonding state, from the same geometry, pen is trying to escape me, we would expect those to be here on the outside, which has important knock-on effects later. So if we take our double bond, which we'd normally draw just like this, if we take our double bond, it's not two bonds side by side, it's a bond in the middle and another bond on the outside, half a bond on the top and half a bond on the bottom. More importantly, or equally importantly, if we want to attack this bond with some electrons, we would have to put the electrons in from this angle, or from this angle, or obviously on the other carbon. I like to think of this as looking a little bit like a banana on the top and a banana on the bottom. If we take a triple bond, we would have another one of these at 90 degrees on the top, on the front and the back of this molecule of acetylene. And that would also have antibonding orbitals on the end here. So now I would like to say a little bit about how we draw reaction mechanisms. So let's take a simple reaction, a simple inorganic chemistry reaction. We've got H plus in solution, we've got Cl minus in solution, and we're going to react them together to make hydrogen chloride gas. It happens in hydrochloric acid, it evaporates as hydrogen chloride, so we need the molecule to form. If we take the two electrons from chlorine, so let's draw the electrons on there, there's two electrons on there. If we take those two electrons and we put them in between the hydrogen and the chlorine, one of them stays mostly connected to the chlorine, but one of them effectively becomes part of the hydrogen, and so the chlorine donates one charge. Whoops, let's leave it like that. The chlorine donates one charge to the hydrogen. We need to draw an arrow to show the electrons moving, and the arrow has one arm for each electron. So we have two electrons moving into the bond, which goes to HCl. We can draw it in the other direction to break the bond as well. So we take our hydrogen chloride and we break the bond. The electrons come out of the bond, so it's important to draw it coming out of the bond, and they're always curly arrows, and it ends up on the chlorine. And this has two arms as well. One arm that says the electron that came from the chlorine goes back to the chlorine, and the other arm says the one that came from the hydrogen ends up on the chlorine as well, leaving us with a hydrogen that's unhappy, so that is plus a chloride ion. If we have the reaction that we drew before with two chlorines, let me get rid of this first. If we have the reaction that we had before, wondering why my board is scratched. If we have the reaction that we drew before with chlorine breaking up to form two chlorine radicals, we need one half an arrow, so an one-armed arrow coming off onto one chlorine atom, and another half an arrow coming off onto the other chlorine atom, which goes to, arrow going to, which goes to 2Cl dot. As we had before, they're not charged because they got the electron back that they had to start with, but they are special, so we need to show that with a dot. That's an unpaired electron, an electron that's left over that usually would be paired up. We need to show the light coming in, and we typically do that with also an arrow, with a wiggly arrow in this case. Let's give it an arrow on the end, and it's usually given the symbol H nu to show that it's light. In this case it would be green light. green. I don't remember the wavelengths. Typically you would write the wavelength of the light there so that somebody can do it again.